Question 1a. The two-dimensional position vector r bar of a ball projected at an angle theta above a flat horizontal surface as a function of time is given by r bar equals vx0t x cap plus vy0t minus half gt squared y cap, where r is measured in meters and t in seconds. Find the velocity function. So here in this question, they have given us the position function r bar in vector form, which is vx0t x cap plus vy0t minus half gt squared y cap. And we need to find velocity function from this. Now, this is an example of projectile motion because the ball is projected at an angle theta. And we know in projectile motion, the x and y component of velocities are independent of each other. So I can find the x component of velocity by simply taking derivative of just the x term for r and y component of velocity by taking derivative of just the y component of r. So we can write for the x component of r as just x, which will be equal to all the term which is with x cap. So that is equal to vx0t. And I can find the x component of velocity by taking time derivative of this term, dx by dt. So we get this as derivative of vx0t over dt. Now, when you take derivative with respect to time, any term which is not time will be considered as a constant. So whichever term which is not t is a constant. So here vx0, the initial velocity component will be treated as constant. And derivative of just t will be 1. So I get x component of velocity to be equal to vx0. We do the same thing with the y component. We will write the y component of position as all the term with y cap. So vy0t minus half gt squared. Then we can find the y component of velocity by taking derivative of y with respect to time t. So that will be equal to derivative of vy0t minus half gt squared. Again, any term which is not time t will be treated as a constant. So vy0 here is a constant. We keep it as it is. Derivative of just t is 1 minus half and g are again constant here because they are not time t. We keep them as it is. Derivative of t squared is 2 times t. Then when we solve for this, we get y component of velocity to be equal to vy0 minus half and 2 cancel each other, gt. Then we can write the final velocity function v bar to be equal to vx x cap plus vy y cap. That will be equal to x component of velocity is vx0 x cap. Y component of velocity is vy0 minus gt y cap. So this is the velocity function for the ball projected at an angle theta. Question 1b. The two-dimensional position vector r bar of a ball projected at an angle theta above a flat horizontal surface as a function of time is given by r bar equals v cosine theta t x cap plus v sine theta t minus half gt squared y cap, where r is measured in meters and t is measured in seconds. Find the acceleration function. So here in this question, we have been given the position function in vector form, which we write as r bar t equals v cosine theta t x cap plus v sine theta t minus half gt squared y cap. We need to find acceleration function from this position. So first we will find velocity by taking derivative of position function. And then we will find acceleration by taking derivative of the velocity function. So we are going to differentiate this 2 times. One to find velocity and then to find the acceleration. I can write the x component of position as just x, which will be all the term with x cap. So v cosine theta t. Then we find the x component of velocity by taking derivative of this term. So derivative of v cosine theta t over dt. Since we are taking derivative with respect to time t, any term which is not t will be treated as a constant. So v cosine theta here is a constant. We will keep it as it is. And derivative of just t is 1. So the x component of velocity will become v cosine theta. After you find the x component of velocity, we will find the acceleration. X component of acceleration will be ax, which you can get by taking derivative of velocity with respect to time, which is equal to derivative of v cosine theta. Now we're taking derivative with respect to time. So any term which is not time will be treated as a constant. V cosine theta is a constant which is not multiplied with time. And derivative of such constant is equal to 0. So I get x component of acceleration to be 0. We do the same thing to find the y component. First, we separate the y component of position. We write it as y equals all the term with y cap, v sine theta t minus half gt squared. Then we find the y component of velocity by taking derivative of this term. So that gives me v sine theta over here is a constant and we keep it as it is. Derivative of just t is 1 minus half g is a constant, so we keep it as it is. Derivative of t squared is 2 times t. So we get y component of velocity to be equal to v sine theta minus half and 2 cancel each other, so we get gt. After you find the y component of velocity, now we can find the acceleration by taking derivative of this. So we get ay to be equal to derivative of vy with respect to time t. The first term is v sine theta. So it is a constant which is not multiplied with time, and derivative of such constant is equal to 0. Minus g is a constant here which is multiplied with time t. So we keep g as it is. Derivative of just t will be 1. So I get the y component of acceleration to be equal to negative g. Now the difference between this constant v sine theta and g over here is g is multiplied with time. So when I take derivative of this term, I keep g as it is. We don't make it 0. Whereas v sine theta here has no time component at all. It is not multiplied with time t. So derivative of a quantity which has no time in it will be 0. So once we find the x and y component of acceleration, we can write the acceleration function as a bar equals ax x cap plus ay y cap, which is equal to 0 x cap minus g y cap. So my acceleration function will just be negative g y cap, which is true for projectile motion. As in projectile motion, the x component of acceleration is 0 and it has acceleration only along the y-axis, which is acceleration due to gravity g. And this acceleration is directed downward, hence the negative sign.